Okay, so welcome. Today we are going to be talking about ground launch projectiles. So first of all, let's define again what a projectile is. A projectile is an object that is thrown into the air with some initial velocity. So some initial velocity. And the key to this is that it could be launched at any angle. So up until this point, we've been talking about when objects are thrown horizontally. So the angle would be 0 to the horizontal, or you could say it's 90 degrees to the perpendicular. But the point of this is that we can even handle, we have enough math background that we can handle it at any angle. And the other important thing is that since we're ignoring air resistance, it's in free fall after that. And so what this means is that when this object's in the air, the only force that we're considering is the downward force of gravity. So the free body diagram for the entire flight would look something like so. So let's say we had this soccer ball and it was launched at 12 meters per second, so this is a given, and it was at 30 degrees. So what we want to figure out is what is this x component of the initial velocity, and what is this y? So I'm going to call this vi in the y, and then this is my vi in the x. So notice that of my 30 degrees is right here, so there's my 30, that the viy is opposite of the 30 degrees, so that would set up my sine. So I could say sine of my angle is my initial velocity in the y over my initial velocity, my hypotenuse. And then the Vix is the adjacent side to the 30, and then I know the hypotenuse, so that's going to do a cosine. So cosine of theta equals Vix over Vi. So notice that for both of these, to figure out the initial velocity in the vertical and the horizontal, I'm just taking the initial velocity and multiplying it by either the cosine of the angle or the sine of the angle. So for the vertical part, which is over here, Vi in the y, this is my 12 meters per second times my sine of 30 degrees. And if you guys remember from your math class, sine of 30 is a half of 12 is 6. This works out to be 6 meters per second. In the horizontal, my initial velocity in the horizontal is my cosine of my angle times my initial velocity. So this is my 12 meters per second times cosine, in this case 30 degrees is my angle. And that works out to be 10.4 if I round it to 3 sig figs. 10.4 meters per second. So moving on, what do we know about this object in the vertical and in the horizontal? So first off, in the vertical, we know that whatever velocity it's launched at vertically on the other side of this, when it lands on the other side, since it's going to rise the same amount that it falls, assuming this is level ground, this is important, that this initial velocity in the vertical is going to be equal to my final velocity in the vertical. My acceleration is negative 9.81 meters per second squared. Once again, this is true for horizontal projectiles and ground launch projectiles. And then the vertical speed in the vertical, this is important, key, will be 0 at the maximum height. And then we also know, and this is the same thing when we throw something straight up, that the time it takes to get to the top is half the total time in the air. So you'll be using this relationship between the two quite often. And this is, once again, this is the same thing that we saw with throwing 1D kinematics, so throwing an object straight up and coming straight down. If it took 2 seconds to get to the top, it'll take another 2 to get to the bottom, so total 4. Time to the top is 2, time to the bottom is 2. The vertical distance is what we call the maximum height, or the time when it's at half the total time. It's what we call at a maximum height. So when we're talking about vertical distances, often we refer to it as a height. And what we'll see in a second is that horizontal distance we often refer to as a range. In the horizontal, once again, if we go back up to our free body diagram, notice that there's no forces horizontally, so there's nothing to slow it down, nor is there anything to speed it up. So the acceleration in the horizontal is 0. And then the initial horizontal velocity on that same line is constant, meaning, once again, whatever velocity, so in this case, the 10.4, that's going to stay the same the entire time in the horizontal. So let's look at a two-dimensional motion map. Okay, and I'm going to do the horizontal velocity in orange here. So we know that the horizontal velocity will stay the same, meaning it will have the same magnitude, the same length, the entire time. So I'm just eyeballing this here, but if you'd like, you can get out a ruler to make sure that the lines are the same length. But then in the vertical, we'll do this in red, we know that it's initially going up and it's going to be at its maximum vertical speed at the beginning. It's going to get smaller and smaller, and eventually at the top the vertical component is 0. But on the way back down, since these are at the same height, it's going to be the same magnitude but the opposite direction. And once again, I'm not getting crazy about the length. These look roughly the same. And then like so, and then we have a larger one. And once again, this red line over here is the same as this red line over here in magnitude, but just opposite in direction. Alright, so let's take a look at an example here. Let's do another color here. So a baseball is hit with initial velocity of 35 meters per second, so my 35 is in my horizontal. That's going to be my hypotenuse. So there's my 35. And then we can break it up into my initial velocity in the vertical and my initial velocity in the horizontal. So the first part is just to sketch its path. So I know it's going to take a parabolic arc, so it's going to look something like this. Maybe you guys can do a better parabola. Well, that's actually not too bad. And the first part then is, or the second part rather, is to figure out the vertical component of the initial velocity. So as we saw before, VIY is equal to VI times sine of the angle. So this is 35 meters per second times sine of 35 degrees. Go ahead, punch that into your calculator. Okay, so I got a value. Oh, I'm sorry, this is sine of 18. So let's erase that here. So sine of 18 degrees. So I got a value of 10.8 meters per second. And while I'm here, I'm actually just going to figure out. Oh, actually, never mind. I don't need to know the initial velocity in the horizontal. If it asks for how far it goes, then I would need to know this piece of information. Alright, so calculate the time it will take for the ball to reach the top of its flight. Explain how the amount of time is related to the total time in the air that the ball will remain in the air. Alright, so here's what I know so far. In my horizontal and vertical, I know my acceleration in both directions, 0 and negative 9.81. Get in the habit of writing these things down. I know my initial velocity in my vertical is a positive 10.8 because it's 10.8 because it's being launched up meters per second. I know that the velocity at the top, which I'm going to call the final, is 0, and I'm going to find the t up, the time it takes to get to the top. So take a minute, look at your reference tables. What has a VI, a VF, an A, and a T? So I'm seeing the final velocity equals the initial velocity plus a t. We said our final is 0. I'm going to subtract my VI over and then divide by a. My a's cancel out over there, and so I get a t of my negative of a positive 10.8 divided by the acceleration due to gravity, negative 9.81 meters per second squared. So notice now I have a negative divided by negative. That makes me happy. Time is a positive. So we have 1.10 seconds. So that's the time it takes to just get to the top. So that's my T up. My total time, which it also asks, the amount of time related to the total time, is 2 times my T up. So, in other words, it takes 2.2 seconds to reach the ground. And we are making an assumption here, too, by the way, that we're assuming that it's landing at the exact same height. Okay, in other words, this distance, I know it's not the scale here, but this distance is significantly greater than this distance, so we can kind of just make this distance insignificant. Or think about if the baseball player was hitting the bat at the ground, which I know conceptually doesn't make a lot of sense, but it simplifies the calculation. Calculate the maximum height. So the maximum height, that's a delta d in the y, is equal to the initial velocity times time plus 1/2 at squared. So now I know how long it takes to get to that maximum height. So I'm going to use my initial velocity in the vertical. These are all vertical terms. And notice that time doesn't matter whether we're doing the horizontal or vertical. So I have my 10.8 positive times, I'm going to drop my units here, I hope you forgive me, plus 1/2 times negative 9.81 times 1.10 squared. So go ahead and once again try to punch that into your calculator. Make sure this is a negative, so this whole side of the equation will be negative, and you'll add that to this. But I'm getting a maximum height of a positive 5.94 meters. Okay, so why don't you try the next one, and we will compare answers tomorrow in class. Thanks for listening. Have a good night. Bye.
30 seconds off.